Continue. Okay, let's get started here. So welcome everybody to our data mining for today. I'm going to, at least today, maybe the rest of these class sessions, wear my little headset here, since for whatever reason, Zoom is last or occasionally been cutting out audio, and I know it works when I wear this, so I will wear this. And especially since with traveling for Thanksgiving and stuff, I imagine lots of people will be having to watch the recorded versions, and so it's important that the recorded versions actually have audio here. Also, I apologize about yesterday having to cancel the office hours for any of you that were hoping to attend there. We're, so I mentioned it in the GitHub post, but we're in the middle of another faculty hire right now for the data science program here. Goal of this new person when they join the department would be that they would be probably most similar to me out of the other people in the math department doing computational stuff. And most of our applicants that we're looking through very much in this like data mining space. And so I'm hopeful that we'd be able to offer more data mining-ish courses, maybe even, I know this course is already like, has a lot in it and a lot of technical math stuff, maybe spreading out it, breaking it up into 2 courses with more practical stuff interleaved, or doing something with deep learning things in particular, or something along those lines. But maybe not, depends on who we hire. Yeah, Jay. Yeah, it's a good question. So we were doing Zoom interviews yesterday, and they only got scheduled. I think I sent out an email like at midnight. They got scheduled for us just a couple hours before that I sent out the GitHub issue to you all. That apparently professors, not just me, but all professors as a group, we are disorganized. But yeah, so not in those Zoom interviews, but when they come and to an in-person interview, they will be meeting with me in the office for an hour, and we will be, they will be at the whiteboard telling me about all of the stuff that they do, and so yes.
So if we do really well on our final, can we be hired?
That can be your goal, yes. So they will also, it'll probably be the week after Thanksgiving that we'll have at least some people on campus, candidates then. So you all would be invited to that. You'd be able to sit in on their teaching or research talks. The research talks definitely going into all of the stuff that we've been talking about in class here, and building off of it in some way. So I'll let you know as those things come up. But the main thing I want to highlight here is that to make up for you all that I had to cancel these office hours, I think the week after Thanksgiving is the more important week than this week to have more availability for you all the week before finals. So I will have make sure that I have lots of additional office hour times / final review session times that last week of class before finals. Today in class, so there is a new packet up here. It is our last Model Zoo packet, Model Zoo 3. This will be the second to last packet that we will talk about. These Model Zoo notes, again, sort of a little bit diverging from where the textbook was. We took a break in the middle of chapter 4. The very last packet will go back to chapter 4, finish up that chapter in the textbook. And then my goal is that we'll finish all of that stuff before Thanksgiving. We might not quite finish it all before Thanksgiving. There might be a little bit more after Thanksgiving that we have to do. But the goal is that the after Thanksgiving time is a chance for us to just review all of this stuff. Again, highlight the important things that'll be the things that you want to definitely take away from the class, definitely know going into the final, and do final exam practice sort of exercises. So that's the goal. Again, yeah, the Model 3 Zoo Notes printed copies up here. Electronic version is this Notes 3 nearest neighbor.pdf in the Topic 6 folder. Any questions about anything administrative in the course? Everybody likes the new desk layout? 4 rows instead of 3?
No.
It feels a lot more cramped. Yeah. There's a lot of space over here. I don't know why somebody changed it like this, but they did. Okay, so yeah, we're gonna get here to the Model Zoo 3 here in just a minute, but we have a little bit more to finish up with the Model Zoo 2. So we'll start off with a quick review of what we talked about last time, and then finish up this note packet before going into the Model Zoo 3. This, the relationship between these two models, we talked about the decision trees and the ensemble methods in this Model Zoo 2 notes. And the main important thing here is that decision trees combined with these ensemble methods is state of the art for a lot of tasks right now. Basically, any task that is not computer vision or natural language processing, decisions trees with ensembles is state of the art for. Concrete examples of that are the very first motivating example we had in this course was about determining whether we should give a loan to somebody or not at a bank. Vast majority of bank machine learning algorithms are decision trees combined with ensembles, and that's what they're using to determine who gets loans, what your interest rate is going to be on that loan, and so forth. Also for medical applications, vast majority of medical applications are either using decision trees by themselves or decision trees combined in an ensemble. So we finished all the stuff about decision trees here. There's a handful of problems again here to work on as review for the final exam. And then we started talking about the ensemble methods. And actually, maybe one last to this on the first notes packet, and again in the scikit-learn documentation, there's this image down here, which shows us the decision boundaries of all of the different models that we're talking about. And we talked about, again, the decision tree last time. It has a lot of these very sharp edges inside of it, which makes it good for this tabular data, but not good for the image or textual data. One of the differences between the decision tree and so random forest here and AdaBoost, these are both examples of these ensembled methods with decision trees as the base classifier. One of the differences between these is that the decision tree has very both sharp decision boundaries in the sense that there's a lot of corners inside of it, but sharp in that there's a very steep change between the dark red and the dark blue. The random forest or the AdaBoost, these are both, again, ensembled methods, ensemble decision trees. They have much more gradual decision boundaries between the red and the blue, and so you can have some more measure of confidence. Like the very dark blue, the model's very confident that that should be a blue label, but the lighter regions, there's less confidence about what it should be labeled as. So it's one advantage maybe to keep in mind of these ensemble algorithms. They naturally give us a way to talk about the confidence of our labeling. Comparing again to, say, the neural networks, the neural network you can see has a lot of very smooth lines going on over here. The naive Bayes and the QDA, quadratic discriminant analysis, these are both smooth lines again because they are the perceptron with the polynomial kernel of degree 2. And those smooth lines tend to not work on data that has this CSV structure. You want that like sharp edges everywhere for that tabular data. Okay, so coming back over here, the ensemble methods. Let me zoom back in now a little bit. This is our hypothesis class for ensemble methods. Again, most of the hypothesis classes we have talked about. We've used the letter H for the name of the hypothesis class. It's customary, though, for ensemble methods to use the letter L for the hypothesis class. And this hypothesis has two of these hyperparameters as inputs to it. The B right here is our base hypothesis, the model that is being ensembled together. And then the T is the number of times we are combining them together. And this H again here is an element of B. There are T of these entries, T of these elements of B, T of these base hypotheses. And so these, if we're saying ensembling trees, each one of these H's right here is a decision tree. But this H doesn't have to be a decision tree. It can be whatever you want. It could be a neural network. It could be a perceptron. It could be logistic regression. Any other possible hypothesis class can be boosted this way. One of the things that I like to do when I am seeing a new hypothesis class like this is compare it to the other hypothesis classes that I already know. And to me, this hypothesis class looks an awful lot like either a perceptron or a neural network. The perceptron, again, we had this linear function about W times some vector H, or sorry, W times some vector X. And here we're, instead of doing W directly times X, we're doing W times a transformation of X, where this transformation right here is a hypothesis class. But if we were to change this X, if we were to change this H, change H to our phi functions, then this would just look exactly like the perceptron hypothesis class. So one way of thinking about ensembles is that it's like taking whatever your base hypothesis is, using that as a feature generation method, and then shoving those feature generation methods into a perceptron. Another way of thinking about this is that it's very much like a neural network. Here again, the way we talked about neural networks in our previous lecture, maybe 2 lectures ago now, was that instead of having a fixed phi function for the neural network, we were going to learn that phi function from the data somehow. And here, these H classifiers in ensembles are typically also learned from the data. In neural networks, the neural network, or the other key phrase, the other way of key name for this hypothesis class was the multi-layer perceptron, MLP. We had a linear structure for phi. Phi always had some sort of structure where it was a big W matrix times an X with a non-linearity in front of it. And so if our base hypothesis here that we are using, H right here, if that base hypothesis is a linear hypothesis like the perceptron, then the ensemble method, very, very similar to the multi-layer perceptron. The ensemble method, though, is a little bit more general because this base hypothesis H here can be anything, doesn't have to be a linear function or like a logistic regression or perceptron. The H could be, again, H is most commonly a decision tree or a decision stump. And if you do this, if you do use a decision tree or decision stump, then you are sort of breaking with this analogy about the multi-layer perceptron, not using a linear feature, not using a linear base hypothesis, but using something a little bit more complicated. And so the ensemble methods with the trees will be able to compute functions that are very different than neural networks. Yeah, for, again, all of these different models, there are lots and lots of equivalent ways of thinking about them, and looking through these, reading through the references will give you a handful of other different ways, equivalent ways of thinking about them. And most people find one of them to be intuitive. I'm sharing with you all the ones that I think are intuitive, but you can look through the references again to see if there's something that's maybe more intuitive to you. The important things for the final exam are going to be all these lemmas and facts that I've listed down here, like especially the VC dimension calculations. And the final exam, you're going to have to be making decisions about what sort of hypotheses, models you're going to be using in different situations. And so you'll need to have all these VC dimensions down pat for all of these different models. The key thing here for our ensemble methods is that it's linear in T, the number of classifiers you're combining together, and linear in the complexity of those base classifiers. So the T right here, the number combined together, the B, the base classifier, so the VC dimension combining T and DVC of B together. And that's where we left off last time. So now we're going to talk about this fact one right here. And that's that there are two basic types of these ensemble methods, boosting and bagging. Boosting, by far these days, the most popular of the ensemble methods. And XGBoost here in particular, this is the thing that is the most common algorithm for Kaggle competitions. In the time frame of around, say, so XGBoost was invented in 2014. In the time frame between, say, like 2017 to 2020, XGBoost was won like over 90% of all competitions hosted on Kaggle. These days, it's doesn't do quite as well on Kaggle. That's not because it's not as good anymore. It's just because Kaggle has realized, everybody's realized, XGBoost totally dominates everything related to tabular data. And so they're coming up with competitions that aren't tabular data anymore, things that may be better for deep learning systems. Okay, so high level, well, maybe I'll also add, so these ones right here, these that I'm underlining in blue, these are the scikit-learn. Okay. Scikit-learn names of the models. XGBoost is its own external package. It's not related to scikit-learn, although it is compatible with scikit-learn. And LightGBM, same thing. Its own separate package. Both of these separate from scikit-learn. LightGBM is also a really good version of these boosting algorithms. XGBoost is a little bit more popular than LightGBM because it's just a little bit faster to train, but the actual like hypothesis class and details of what it can do are basically identical. I don't know of anybody who's a practitioner in industry who uses either of these AdaBoost or gradient boosting classifiers from scikit-learn. Practitioners in industry generally pick one of these two libraries over here. These, again, scikit-learn came about as first graded in 2011. So before XGBoost and LightGBM, both of these models right here implemented, but they're more or less out of date at this point. Okay, so what exactly is boosting? If we come back up here to our hypothesis class, in boosting, we learn both this W parameter right here and the HT parameter, both the W and these models at the same time. There's a lot of details about how exactly to do that I'm glossing over, but you learn both WT and HT at the same time. The HTs here are base hypotheses. These are always going to be trained on some subset of the data. That exact subset is different between various different algorithms. But this HT, it's not trained on the entire data, trained on some subset of the data. The important thing here is that we're learning both WT and HT, and because of that, we get the full complexity, the full power of our hypothesis class. The full complexity or power of the hypothesis class. And yeah, so that's a very intuitive level statement. The making that a little bit more formal is that any instance of this hypothesis class, any hypothesis in this hypothesis class is something that the model is, or the training algorithm is somehow considering and either using or rejecting. Any one of these functions ends up being a perfectly valid function that the model might consider. And so the like in practice DVC dimension, generalization error follows all the things that we've been talking about from chapter 2. Bagging, the difference between bagging and boosting is that in bagging, the WTs are not learned. WT is not learned. It's typically set to 1, although it could be a random value as well. And the intuition about this, if you do this, if you make all these WTs be constant values or something that's not learned from the data, the intuition is that this formula up here, this summation, becomes kind of like an average. You could, in fact, add a 1 over t out front here in order to make it an actual average, and it wouldn't affect anything because of the sign function would be indifferent to that scaling factor. And so if we make all these WTs right here, it's like if we make them all equal to 1, it's like we're just averaging, literally doing a straight average of all of these HTs together. So it's averaging a bunch of base models together. And because of this, there are many hypotheses in this hypothesis class that if you use one of these bagging methods, like the bagging classifier or the random forest classifier, there are many of these hypotheses that you will not actually ever be able to learn. Anything that has a hypothesis where the W value is not equal to 1, you won't be able to learn it. And so this constraint right here doesn't actually affect the actual VC dimension, but it does affect the generalization error that we observe in practice. No effect on the DVC, but a practical effect on the generalization error. And that practical effect is that the generalization error goes way down. In the scikit-learn documentation or most explanations about bagging, the particular language that they will use is they will say that the variance goes down. And that has the exact same meaning. When they're talking about the variance, they're referring to what Leon Bateau called that estimation error. Which is, again, I'll draw the plot for us. So the x-axis here is the number of data points, and there's a solid line going across like this that looks something, what that is that's our approximation error. Approximation error for the hypothesis class. That's the best error that we could get given an infinite amount of data. And the estimation error is approaching the approximation error as n gets larger. And so it's this quantity right here. When they're talking about the variance, it's that quantity that goes down. Yes?
Do they like visualize the difference between boosting and bagging? Like, for example, if H was B2, where like not only will it like figure out the circle, but also maybe like the size of the circle, but bagging would just figure out what the circle.
Yeah, so the question is about figuring out like how does all this relate to the decision boundary, and how can we actually visualize this? So we do have a visualization over here about the difference between so AdaBoost is one of these boosting methods, and in particular they're using AdaBoost with a decision tree. Scroll over. There we go. AdaBoost right here is one of these boosting methods. The random forest is the equivalent bagging method. Both the random forest and AdaBoost right here are using this decision tree classifier as their base method. And the question is like, can we get some better intuition about, I don't know, what these decision boundaries are going to look like? And the answer is they're not really. There's no good intuitive explanation at the decision boundary level. That if you look at these pictures right here, you can see, okay, maybe the random forest looks like it's more confident in different locations because it just has darker values. That's not a principle that's going to hold in general, though. It's easy to come up with data sets where the reverse of that is going to be true. And you have some situations like on this circle data set right here where it looks like the bagging classifier does pretty well, but the boosting classifier on the right-hand side is not doing as well. You can see that there's blue areas over here that look like they should probably be red areas and not blue areas. The classifier doesn't have a lot of confidence in that, but it is making a big mistake over here. My sense is that that's not something that's intrinsic to boosting, though. That's just when they made this picture, they happen to not have a good hyperparameter tuning going on. That this model over here is clearly overfitting its training data, and with better hyperparameter tuning, you would get a decision boundary that looked more like this over here. And then so down here with this linear decision boundary, you get like, I don't know, it kind of looks like boosting and bagging are opposites of each other. Dark values in the top left, light values in the top left over here. That's just an artifact of randomness and not something inherent to the models. So there is no real good way of visualizing the difference between AdaBoost and random forest, or in general between any boosting method and any bagging method at the decision boundary level. The one thing that we can observe, though, is comparing both of these two boosting methods right here to the base model decision tree and seeing that the decision tree does have these, like, there are no regions or very few regions of mild confidence in its predictions. And the ensembling these methods together, sometimes people anthropomorphize these models and will say that ensembling makes the models more humble, that you get these like these lighter regions where the model is less confident in its prediction. So the models boosting and bagging both more humble than the decision tree over here. But we can't really say anything about the difference between the two of them. It's a good question. The right kind of question to be asking about these sort of models is, how can we actually visualize these? What exactly are their differences? The answer, though, is that we can't, that we just have this trend that we can observe right here, is that if we are doing the boosting version of this, then we are taking advantage of the full complexity of the hypothesis class. And so in particular, like this VC dimension is really the thing that is controlling our generalization error. But if we have some sort of extra restriction on our hypothesis class, you can, in some sense, think of this as like those hard order constraints about constraining what this W value is allowed to be, making that hypothesis class smaller. That is going to reduce our generalization error. We could rewrite or create a new hypothesis class of bagging that has this additional constraint inside of it, that all of the W's must be equal to 1. At that point, it becomes clear that the bagging is a subset of boosting, and so bagging is going to have the higher in-sample error and the lower generalization error. But yeah, in practice these days, Nobody uses the bagging classifiers for anything. It's something that is, at this point, just of theoretical interest, and people who are using ensembles strictly boosting, and 90% of the time XGBoost. Good question. Okay, the last part of this document here is this problem 4, which just has some practice problems for you of going through these VC dimensions and doing some basic calculations with that. So I will leave that for you all to do on your own. And we will switch next over to the model Zoo 3 over here. And we will talk about two new methods here, nearest neighbor methods and the support vector machine. We've already talked a little bit about the support vector machine when we talked about optimization and comparing it with logistic regression, but we're going to talk in more detail about it today, maybe next class period, and see how it's very closely related to this nearest neighbor method up here. This note that I have at the top of this Model Zoo 3 notes has a link to this, so amlbook.com. This is our textbook's website. Our textbook has what the authors call e-chapters that are, for whatever reason, not in the actual printed book, but in their book.com. I forgot to get the link. There we go. But it's on their website, and you can download these if you would like. All of the models that we've talked about do have an e-chapter in the textbook here that you can look at. The textbook versions of everything is much more mathematically technical than the stuff that we've talked about in class, and so you don't need to look at these references if you don't want to. With the exception of the similarity-based methods right here, so this is the nearest neighbor. They do have a pretty good intuitive level explanation of nearest neighbor here, and so that would be a good one to potentially look at. But the other one's very, very technical, and so not needed, unless you like to do that, in which case you're welcome to. Okay, so nearest neighbor. This is one of the original machine learning methods, goes back to probably forever, but it has at least been described formally since the 1700s, and it's a very obvious sort of classifier here. I'll draw a picture here of a data set. This is at the data set level, this picture, so this is X1 and X2. These are not a picture at the weights of a model. These are a picture of the data set itself. And I'll draw so a bunch of pluses. We'll do a sort of complicated shape, this crescent shape that we've seen before, and I'll do it in different colors too, so highlight the difference between the pluses and the minuses. And we've seen some examples about how the perceptron, the linear hypothesis class, is not going to be able to do well classifying data in a shape like this. And we don't know exactly what the perfect feature map would be for this. And so we saw some examples about how the neural network could learn a feature map that would project this into a linear space, and then we could use the perceptron via the neural network to do that. Another way, more obvious, intuitive way to do this is with the nearest neighbor classifier. And in the nearest neighbor classifier, whenever you have a point that you're trying to classify, say this point right here, if it is the one nearest neighbor classifier, then you find whatever is the closest point, in this case, this one right here. And because this is a negative, you decide that this point should also be classified as negative. Similarly, if we had a point over here and it's closest to the positives, so that should be classified as a positive. In between over here, if we had a point like right here, it's closer to the negative than to the positive, so that would be a negative point, but this point right here, closer to the positives than the negative, so that would be a positive right here. So this is a very intuitive classifier and widely used still today in many domains. Yes, question?
Where does the K factor in?
Yes, so what I described was the one nearest neighbor so far. And the question is, where does the K factor in? So we talked about the one nearest. neighbor. All the stuff that I talked about in magenta here was the 1 nearest neighbor. So this k right here is a variable. I've set it equal to 1. In the general k nearest neighbor, what we're doing is instead of looking at the closest 1 point, we look at the closest k points. So if I'm at, say, this point right here, and I want to look at the 3 nearest neighbor of this point, depending on exactly where I draw it, the 3 nearest neighbors could be those 3 points right here. And so this would be labeled as a negative in the 3 nearest neighbor case. That's the 3 nearest neighbor. Intuitively, when we increase the value of k, we're going to reduce our sensitivity to noise. So k goes up, implies noise is less of a problem. To see why that's the case, let's say I'll draw in green here a noise data point. Oh, I'll keep it in red. A noise data point over here, a plus right here. And this, for whatever reason, we know is just obvious noise that our data, like the pluses need to sit over here and the minuses over here, and this is just somebody's made a mistake somewhere. If we're using the 1 nearest neighbor algorithm, then all of this plus here like makes everything and all of this region be a plus. And so this 1 noisy data point greatly changes my decision boundary. But if I'm using the 3 nearest neighbor, then this 1 plus over here will not change my decision boundary at all, because no matter which point I select over here, I'll get 1 plus inside of it, but then the next 2 data points will be minuses. And so with 3 nearest neighbor, this region remains all negative. So the reason people would use 1 nearest neighbor is because it's maybe the most intuitive, obvious to explain. Here's just your 1 similar data point, take that same classification. But the reason people use k nearest neighbor with a larger value of k is it makes you more robust to noise and to outliers in the data. Okay.
For the k nearest neighbor classifier, would there be any scenario where you would add weights to like the farther?
Yeah, it's a fantastic question. So there are many variations of k nearest neighbor here, and the most straightforward, obvious thing to do is to just weight everything equally. So like this data point here, weight all 3 of these data points equally. That is available in scikit-learn. Another option that's available in scikit-learn is that instead of weighting everything equally, weight it by the distance to this point. And because this point right here is really close to this plus, maybe I should think that it is like weight this plus more heavily and ignore or downweight these 2 minuses. And so this might end up being classified as a plus in that case. So that is something that people do and consider, and you can do with scikit-learn. In practice, though, it doesn't really have any effect on your decision boundaries. And so for the most part, people just do the simpler, easier to explain thing of here are your k nearest neighbors and weight them all equally. That's a good question. Any other questions so far? Andrea?
When we increase k, is that increasing the model complexity, or is it?
Okay, yeah. So that's a great way of thinking about this problem. We're learning a new model right here, and one of the things that we want to know about models are how complex are these models, and both in terms of our runtime and in terms of our statistical properties. So we're first going to talk about the runtime here. The runtime is really easy to talk about, and then we'll talk about the statistical properties. For the runtime, there are 2 basic methods of implementing this. The first is brute force search, where you basically have a for loop over all data points, calculate the distance between all data points, and then take the smallest factor of k. Brute force has a runtime of theta of d times n. D for each one of your distance calculations takes time linear in the number of dimensions, and you have to do exactly n of those calculations. Notice that k is not inside of that runtime in any way. There are also, however, data structures that you can use that can be used to speed up this search. And so instead of brute force search, there I'll just write clever data structure. The goal of this clever data structure is to make the nearest neighbor search take logarithmic time. So say each search take time O of log n. But in general, this turns out not to be possible. And in a lot of specific cases that we're interested in, it is possible, but it's extremely, extremely technically difficult. In order to even describe one of these data structures and understand the implementation, I'll say that, part of my own research has been on inventing some of these data structures. I was in my third year of my PhD before it even made sense for me to start thinking about how these data structures are implemented. That this is among the most complicated math that I have ever worked with. In practice, so that's our goal. Sometimes it can be realized, sometimes it can't. In practice, there's a very bad penalty on our dimensionality here. And the practice looks something like O of exponential in our number of dimensions, and then sometimes log n. So this is closer to what data structures do in practice. And this runtime that's exponential in the dimensions right here, blue, this is often referred to as the curse of dimensionality. There are other curses of dimensionality. We'll see another one here in a minute. And there are lots and lots of lots of ways people do these clever data structures. In scikit-learn, there are two possible data structures that can be used in scikit-learn. I'll do it right here. Scikit-learn is all together. It implements something called a ball tree and a KD tree. And the guarantees on both of these are that the runtime is O of 2 to the D times n. So the guarantee is that it is worse than doing the best possible clever data structure, the best dimensionality here, and the best, the guarantee is that it's just worse than everything. In practice, it's not always this bad, but this is the guarantee that those data structures provide. Vast majority of real world situations, n is small enough and d is large enough that the brute force strategy is what most people use for most nearest neighbor strategies. So that's the runtime complexity. The next is the statistical complexity. And so we'll break that down here into a couple of parts. The first part here, fact one, is about the in-sample error of using one nearest neighbor. And the claim here is that the in-sample error of one nearest neighbor is always equal to 0. To explain intuitively why that's the case, I'll just real quickly scroll back up here. And if you take any one of these data points, say this point right here, and you find the nearest neighbor of that data point in this data set, you're going to get that same exact data point, and it will always have the correct label. And so that's why the in-sample error is just trivial equal to 0. An immediate implication of this is that you can shatter any data set always. And so the VC dimension here, DVC, is infinity for one nearest neighbor. It's also infinite for k nearest neighbor, but it's not as obvious to show that. Yeah, so because the VC dimension is infinite, that implies that all of our discussion about generalization error and VC dimension can't be used to talk about nearest neighbor. So say the E in minus E out, this whole theorem equals O of square root dVC over N. Basically, the whole point of our second midterm is useless for nearest neighbor. Doesn't apply to nearest neighbors. Useless for nearest neighbor. And instead, we have somewhat similar, but also very different bounds in this theorem 1 right here. And I'll talk about the details of these bounds here, go through what these equations mean here in a second. But first, I just want to highlight that like this VC dimension analysis, this is a general analysis, works for everything. But again, it was focusing on worst case scenarios about data points. We were talking about that like it only has to be able to shatter one data set of a particular size in order for the VC dimension to be that size and be very large. It's not like an average case analysis or a best case analysis. This is more like a worst case analysis when you're using VC dimension. The theorem 1 down here, this is more like an average case analysis, like what we see in practice. And in particular here, this theorem is, I wrote it out a little bit informally because exactly what it means to be a well-behaved data distribution is hard to describe. The textbook does describe that in a little bit more technical detail, and it's really a lot of gory detail in this link right here if you wanted the gory detail. But this bound right here is based on a particular data set. The VC dimension bound up here, this is for all data sets in principle, and this bound down here is something for a particular data set. Okay, that said, let's walk through the details about what this bound is telling us. There's 2 equations here. We'll start with the top one. This top equation is specifically for the one nearest neighbor hypothesis. And the first thing that jumps out to me is that we have our E out, our out of sample error here. This is the same thing that we had on the left-hand side above, but now on the right-hand side, we no longer have the in sample error. We also have the out of sample error. But this is an out of sample error of a different hypothesis. This is the out of sample error of f, our true label function. So equation 1 up here, there's sort of 2 implications, 2 things that are going to be important to take away from this. And the first one is that our out of sample error is bounded by twice the Bayes error. So E out of one nearest neighbor of our hypothesis, I'll just do approximate right here, is about twice the E out of our true Bayes function right here. The implication is that if we have no noise in our problem, if E out is very small, then that implies that one nearest neighbor might be a really good strategy to use. But if E out is large, so if E out large, that implies definitely don't use one nearest neighbor. One nearest neighbor, definitely bad. This tracks with the intuition from our picture that we were drawing above, where we said that a single outlier can really destroy our decision boundary with one nearest neighbor. But as we increase the value of k, we become robust to more more noise in that data. And the example we had up above was with k equals 3, that individual noise point no longer affects things. So let's see, the things that I wrote down here in magenta follow a little bit both from the equation 1 and equation 2. I haven't talked about equation 2 yet, so let's go ahead and talk about equation 2. Equation 1 here is a upper bound on our out of sample error of our hypothesis, and equation 2 is a corresponding lower bound of the hypothesis. Equation 2 here is a little bit more general in that it works for k nearest neighbor and not just one nearest neighbor. But in equation 2 right here, if we take this k and substitute in 1, then we get 1 plus 1, so 2. And so our out of sample error then becomes greater than or equal to twice the out of sample error of f. So that provides a lower bound on the out of sample error right here, and then the equation 1 provides the corresponding upper bound, ignoring this extra term over here that depends on the size of the data set. The second important thing, so this is like, if there's one thing to know about nearest neighbor, this is the thing to know. And yeah, comes up all the time in interviews. Again, also comes up all the time in practice because a lot of problems have a lot of noise. Some problems don't have a lot of noise. And depending on where you fall out in the noise spectrum is which one of these two models you might want to use. Or sorry, whether you can use this model or not. The second thing to talk about, so yes, Jay. Yeah, that's a great question. The question is, I thought we could never know F, and I thought we could never know the out of sample error. And so how can we do any of this? So it turns out this value right here, you'll never be able to calculate, this 2e out of f, you'll never be able to calculate that. But still, that's like a value that in the Platonic world of math outside of physical reality exists somewhere. This value for your problem might be 0.12, it might be 0.00. It's something that exists even if we can't know what it is. And so this whole equation out here is something that is going to be true, even if we don't know what one of these individual terms are. And it turns out actually we don't know what either of these individual terms are. We don't know what this term is. We can't know this term right here. We also can't know this term right over here. This term we can't know for two reasons. One is because we can't calculate f, and the second is because we can't calculate the out of sample error exactly, because that requires infinite data. But this term over here we also can't know because it also requires knowledge of, it requires infinite data to calculate this out of sample error. So yeah, there's no contradiction about that because we're not actually calculating these terms. But this is the thing that we're ultimately trying to minimize, the out of sample error for a hypothesis. This is what we ultimately want to minimize for any of our systems, any of our models, any of our data sets that we're working with. And so if for some reason we thought we had evidence, we had suggestions about the out of sample error of f being high, then that would be bad here. It is, yeah, not possible in general to have an exact value of f, but it is possible to have some good estimates of f. So this problem 2 down here talks about the ImageNet data set. We talked a little bit about that last time. And one of the things that I mentioned very briefly last time was that we have an estimate on the base error of this ImageNet data set. That estimate is 5%. And this comes from two places. The first place is that Karpathy, one of the websites that we looked at, he manually tested it himself and he got a 5% error rate. And humans are pretty good at this, so we think that he probably got about as good as any system could conceivably do. And the other reason why 5% seems reasonable is that we know for a fact that there are many labeling errors in the data set. And so even if we did have something that could perfectly classify, we know that it's the Bayes error for this problem is not 0. And so here, what is the best out of sample error that we can expect from a one nearest neighbor classifier? That would be about 10%, about twice the Bayes error by the bounds above. And so again, yeah, we don't know the exact Bayes error, so we don't know the exact best possible situation from a one nearest neighbor classifier, but we know that, or it's very reasonable to assume that getting better than 10% here is off the table with one nearest neighbor. So if your business application requires, for whatever reason, that you're better than 10%, then you don't even bother trying one nearest neighbor. Good question. Yeah.
So if we go back up, are we approximating E out of H with Bayes error then? Like 2 Bayes error?
It is a true statement that E out of H is approximately equal to twice the E out of the Bayes error.
E out of the Bayes
Sorry,
error?
E out of the F function here, which is the Bayes error.
Okay.
This approximation here, again, follows, I'll highlight it in blue, follows from these two things put together. Those two things together are what implies this approximation right here. The other important thing, though, to know about the nearest neighbor is about this term over here. And so that's what we will talk about with bullet point 2 over here. So at first, and actually I remember when I first saw this theorem, I thought that that's actually a really good error rate over here. That reminds me a lot of the VC dimension, because again, our VC bound has the error of the DVC divided by n, and the DVC for a linear hypothesis class, that's going to be equal to D. So the square root of D factor up here, this square root of D factor, that looks pretty good to me. And this n over here, that's where the problems are going to come up with. At first, it looks okay because it is on the denominator. We have the negative sign over here. It's on the denominator. But this fact that the D appears in this term over here is going to be very awkward for us. So I'm going to write here that, let's see, I'm going to zoom out so we can see it both at once. There we go. If we have this term, this n to the negative 1 over d plus 1, so that's this part right here. And we're just going to set this equal to some constant, some epsilon that we want our error to be. So we want this epsilon value to be small, so that we are, in fact, our out of sample error is very close, or twice the Bayes error. If we do that, though, then it turns out that working through the math, E is going to have to be epsilon 1 over epsilon raised to the d plus 1 power. If we want epsilon to be small, say like 0.1, 0.1 is not very small, but make epsilon 0.1, then everything inside the parentheses here becomes 10, and then you're exponential in the size of D. So that's the key bad thing about this second part over here. This is exponential in the size of D. This magenta term that I highlighted right here, that's exponential in D. And that means that as our dimensionality increases, the key takeaway of that is as D goes up, we need n to go up exponentially. And that's a really bad property to have in our learning algorithm. That again, real world applications these days, D is often in the billions. And so 2 raised to the billion power is an absurd number. Some of these practical data sets down here, like so ImageNet, the dimensionality is Typical image taken on a smartphone is about 1 million different pixels, and so the dimensionality here is in 1 million. So nearest neighbor is going to have a very hard time dealing with that from this part of the bound. Yeah, so 2 requirements if you want to use nearest neighbor. One is that you want your Bayes error to be small. The second is that you want your dimensions to be small. In practice, so it's again rule of thumb practice. Rule of thumb. If d is less than 10, less than or equal to 10, I would not be concerned and be okay with using nearest neighbor. But if d was, say, greater than 10, then I would start being very concerned about the this error term right here. And so because of this, nearest neighbor very often combined with either PCA or the random feature projection to to do well. Any questions about any of that? Yeah.
Does this rule of thumb only apply to one nearest neighbors or all?
Yeah, that's a good question. Does this rule of thumb apply to one nearest neighbors or all k nearest neighbors? The lower bound or the reason that this is separated out as being only one nearest neighbor right here instead of all k is because this expression over here becomes even more complicated, even scarier, and even worse in higher k. So higher k makes the this cursive dimensionality even worse. And I mentioned cursive dimensionality up above in the runtime of nearest neighbor, but here's another situation often called the cursive dimensionality. All of this also a different curse of dimensionality. And yeah, the higher k just ends up making things worse in both situations. But I would still basically use this same rule of thumb no matter what the k was. Okay.
Is the DBC or n equals d and the second equation? I think those are like 2 different things, right? We divide something.
Yes, this is my these things unrelated to each other. This was my callback to our main result from midterm 2. This magenta right here is this magenta right here.
When you say callback, is that like specific hypothesis, like this example?
So this is the generalization error always equal to that. And so it's linear in the DVC right here is linear in our D dimension. So the D dimension's inside of a square root. So this part of the square root of D over here, that seems like totally reasonable to me. And this square root of D out front, that is not the curse of dimensionality. That is a very normal and good dependence on dimensionality right here. But yeah, so this stuff in red was related to this square root D right here. And then the stuff in magenta right here related to the rest of that equation over here. And it's, yeah, just not obvious that this means it's exponential in D without doing some, without thinking about it a little bit. But this is the bad part of this equation right here, is that D appears in this spot. This part's good, this part's bad. Okay, so this notes packet has a few more problems over here to practice thinking about the nearest neighbor algorithm. And then the last of these models that we will talk about for the entire semester, the last one of the major models that people care about, is the support vector machine. And there are 3 standard and equivalent interpretations of the support vector machine. We have already talked about number 1 right here. This is, it's come up a handful of times where I've mentioned it, but the main one is in the optimization notes, where we saw the different loss functions, talking about whether they're convex or non-convex, whether they're surrogates or not surrogates. And so this loss function right here has the nice benefit of being convex and a surrogate for the 0-1 loss, and it is the absolute most robust possible loss while maintaining both of these properties. And so it's the most robust. The drawing of that, it looked like this sort of hinge. That's why it's called also the hinge loss, because it's just a straight line that has a hinge inside of it. And this looks very, very close to the logistic loss, which at very large values and on either extreme is different, but it's just smoother here in the middle. The blue right here, this is the logistic loss, logistic regression. And the red line is the hinge loss, or SVM. And because these loss functions are both very similar to each other, SVMs and logistic regression have the reputation of being very similar to each other. But SVMs also have these 2 other interpretations right here that logistic regression does not. So we'll start talking about what it means to be a large margin classifier today, and then next class period we'll probably talk about how this relates to being a smooth generalization of k-nearest neighbor. So, large margin classifier. Let's draw another data set down here with our, these are again the x1 and x2 axes, so we're visualizing a data set right here. And we'll do a linearly separable data set. So since it's easy to visualize, I'll keep the same color right here. And then, so recall that the perceptron model is going to give us just any line, some arbitrary line that separates these 2 classes. And so say, I'll do it solid line, that line here, or that line here, or that line here. These are all valid perceptrons. And the perceptron learning algorithm, PLA, might return any of them. But some of these lines seem obviously better or worse than other lines. And the line that seems obviously the best here is one that goes right down the middle. This line seems like the best. And this is the line that the SVM will give us. So the SVM. And the reason this is called a large margin classifier is because, again, the margin here, often denoted as rho, is the distance between, rho is this distance between our hyperplane that is separating the data points and the closest of those data points. So this Greek letter rho right here, again, is the margin. And one of the properties, if you work through all of the scary math, one of the nice properties of this hinge loss is that it, when you minimize that, it results in maximizing this margin. So this blue line here, the formal way that we know that it's the best is that it has the largest margin out of any of these possible linear classifiers right here. In particular, all of these magenta ones are going to have a smaller margin. So like this line right here has a small margin right there. And this line right here has a small margin everywhere. We talked about the margin previously when we were talking about the runtime of the PLA. And besides the margin, there was one other property that was useful for us, and that was the radius. And so let's remind ourselves what the radius looks like. So we'll do orange for the radius. It's a circle centered around the origin, not centered around the data, but centered around the origin. And it's the smallest circle that contains all of the data. So this right here, R, called the radius of our data set. And we saw when we were talking about the runtime of the PLA that like R by itself, not a important quantity, and rho by itself, the margin, not an important quantity, that it was really the ratio of R and rho that somehow captured the difficulty of the runtime of the PLA. And it turns out that that's true with the support vector machine and our generalization. We're going to scroll down to the next page right here, and this theorem 2 is talking about the VC dimension of the support vector machine. And notice that this VC dimension right here depends on both R and rho. Because the perceptron is a linear classifier, so again, or sorry, because SVM is a linear classifier, SVM is a linear classifier. It also satisfies that the dVC is less than or equal to d plus 1. And so sometimes one of these bounds will be larger, sometimes one of them will be smaller, and you get to use whichever one is smaller, whichever one happens to be better for your particular data set. One of the, interesting things about this theorem right here, sort of uncomfortable things for me from my perspective, is that this theorem depends on the data. This R value and this rho value depend on the data. But the VC dimension is not supposed to depend on the data. The VC dimension is supposed to be like an abstract quantity about our hypothesis class. And the textbook has a, I think, readable explanation about this, about their theorem 8.5 right here. This is their word-for-word theorem 8.5 from the textbook. And so if you share my discomfort with that, you can read their description of it. It's very readable. But yeah, so there's some subtleties here that are going on, but the takeaway is that these are the two important quantities that control our generalization for the support vector machine. What we're going to talk about next time is observe that because this quantity right here, this VC dimension, has no dependence on D, no dependence on D, we can make our dimension, our VC dimension, or the dimension of our features extremely large, and we will actually make them infinite dimensional features, and we will still be able to guarantee great generalization because we can guarantee that we have a small VC dimension even though we have an infinite number of features. It'll turn out that that's really good for problems that cannot be represented as vectors like we've been doing so far. We've assumed all our data points sit in R to the n, and the support vector machine, the main way that it's used these days is for data points that do not have a natural vector structure like that. So we'll finish talking about that on Monday. And if anybody has any questions about anything, I'll stick around and get those answered. Otherwise, yes, see you later.